Hello and welcome. My name is Alexander Huss. Let me first take a second to thank the organizers for the very kind invitation to give this series of lectures at this MITP school. Unfortunately, it has to be done remotely, but I'm very much looking forward to next week, where we will have the opportunity for more direct interaction, and you also to ask quite questions directly to me about things that might have been unclear. Also, don't please hesitate to write me an email. I've read that there's also a Slack channel, so I will make sure to register there so that questions can be also posted on that platform. So I was tasked to give a lecture on jet physics, which admittedly is a very broad topic. Furthermore, after looking at the other types of lectures that I give at the school, this is by far the most phenomenology-oriented one, so I take it as a challenge to try to make this interesting for you. So jet physics. Maybe let's start with the question of what is a jet? If you open up a textbook, the typical definition you would find is that it is a collimated cluster, a spray of jets. That's the important bit, is that it's collimated in some cluster, a spray of particles or flow of energy. And this well describes also the picture that we have on the experiment. So here on the left-hand side, you see the vent measured by Aleph at lab, where we're looking at the process of E plus and minus annihilating into some Z option photon that subsequently decays in the QQ bar, and we quite clearly can identify these two jets in the event. The picture we have on the theory side is shown here on the right. So in a way, what we want the jets to be is a proxy for the underlying heart. So with heart, I mean high energetic partons, which are the quarks and gluons. And the picture we have on the theory side is that these high energetic quarks and gluons, they radiate off more gluons, ultimately hadronize into mostly mesons, so pi plus, minus, pi zero, sometimes kaons. This basically is what is detected on the experimental side, causing this kind of spray. As we will go in a bit more detail later, partons themselves are ill-defined concepts perturbatively. So whereas jets are well-defined if done properly, and as such, these jets serve as like an interface between experiment and theory. So now that we roughly understand, have a picture of what a jet is, why do we care? So as I already said on the previous slide, jets are everywhere as soon as I think about QCD. Given that any parton ultimately converts into a jet, whenever I want to study processes that involve some QCD or colored particles in final state, you inevitably will be confronted with jets and have to deal with them. They also allow us to study quantum field theories and gauge theories. So taking this example of the plus and minus collider from before, we saw this event of two jets where we had this two back-to-back spray of particles, but I can also ask the question of what is the probability of measuring free jets? In this case, I can have the opportunity to actually radiate the quark line to give this free jet configuration, and as such, this serves as like a proxy or a probe to detect gluons or to establish the existence of gluons. Let's put it that way. I can push this further. I try to measure 4 jets in events, and this for the first time will actually also contribute diagrams where the gluon is emitted from the gluon. So this directly proves the non-abelian structure of the theory. So as you can see, by studying these kinds of these different kinds of processes, you are able to more and more gain insights onto the underlying theory and test various aspects of it. Another very important area where jet physics enters is new physics searches. So for instance, if I want to study the Higgs sector, the Higgs predominantly decays into BB bar particles. So if I want to detect that channel, I will be confronted with two bottom quark initiated jets. Also in case of dark matter, by definition, obviously, these are particles that do not interact electromagnetically or strongly. So if I were to produce these dark matter particles at colliders, and only those in a process, then actually I wouldn't see anything in the detector, and as such, I wouldn't be able to trigger on these kinds of events. So what you have to do is you have to somehow infer its existence through something that I can measure. One of the proxies to look for dark matters are so-called monojet searches, because in this case you have a single jet in the event, which is not balanced by anything, which means I have a lot of energy imbalance in a way, which you can then try to infer or look for dark matter in a way that it recoiled against a hard jet. And another aspect of very intense study are so-called boosted objects, where I look at very heavy resonances that decay. And since they are very energetic, the decay products, they are very collimated and can be detected or could end up into so-called fat jets, as we will briefly discuss towards the end of these lectures. So there are various applications of jets physics, which are very interesting. But not only that, they're actually unavoidable as soon as we look at the LHC. So this is the so-called Stairway to Heaven plot. It summarizes in a very neat way the different kinds of processes, which are given at the bottom, as measured by in this case, the Atlas experiment. And what you see first of all is that among all the hard processes, jet production is actually the one with the highest cross section by far. Right? These are really objects that are produced in abundance, and as such, you can really do very detailed tests of QCD. However, not only that, there are also processes which rely on jets in order to define the process itself. So whenever I have a top, it will decay into a bottom quark and a W boson. So I will always have a bottom quark jet in order to identify the top through its decay products. Furthermore, this W boson decays hadronically, the top actually ends up becoming 3 jets, or in the case of a boosted top fat jet with 3 prongs. Another interesting process is this BBF process, where these jets actually have a very distinct kinematical feature that allows us to distinguish the Higgs signal process from the overwhelming background. And last but not least, a lot of processes are also measured in different jet categories. These are the blue lines, blue shaded areas. So in case of W or Z production, these are processes that are actually measured with up to 7 accompanying jets, which is quite impressive. And to see as I increase the number of required jets, the cross section drops. So as soon as you try to do physics at the LHC, basically there's no way around being concerned about jets. So one thing that I wanted to emphasize right from the start is that jets, however, are not unique at all. So here on the left, we have the plot that I've shown you already before, and anyone you would ask how many jets you see in this event will probably just say, immediately say, yeah, these are 2 jets, right? It's quite distinctive. However, when you look on the event on the right-hand side, the situation becomes a little bit more difficult. So you could say, okay, maybe this is a jet that I want. Here, this looks like a jet. This looks like maybe a rather low eject jet. Here it becomes a little bit more delicate. Is this a jet, or is this actually one big jet? So as you can see, there are a lot of different ways of trying to identify jets, even by eye. And there are basically 2 underlying freedoms that you have. The first is the choice of the particles that you decide to put together. So these are the things that I somehow try to circle in these cones. And the second part is how I choose to combine them. So in particular concerning their momenta. I guess one of the most intuitive things in a way to do is to say, oh, I will combine these particles that form a jet by simply adding the four momenta together, and that will be the four momenta of my jet. But this is by far not the only option you have. And there are different ways of doing it. So these kinds of ambiguities have to be fixed, and in doing so, you come with a jet definition. So whenever you communicate some jet results, it is absolutely crucial that with it to specify what definition of jet we have used. There is no complete freedom, so there are a couple of properties that you better satisfy, like infinite safety, and this is something that I will cover in the second lecture. Not only are they not unique, but they're also fundamentally ambiguous. And to make this point, let me bring back this theory picture that we had and our somehow idealized hope that we said we want this jet to be a proxy for this high energetic parton that initiated this jet in a sense. However, when you look on the left-hand side, where we're dealing with a colored particle, whereas on the right-hand side, the clustering is done on color-neutral hadrons. So there's intrinsically a mismatch that you will not be able to iron out. So there's nothing like a perfect jet algorithm, first of all. And the best we can hope for is that somehow the clusters formed on the basis of partons are a good proxy for clusters based on hadrons. And I guess the best we can hope for here is uncertain inequality up to something like the non-perturbable scale of QCD, which is nominal QCD, over the energy of the jet, something along those lines, right? Since we're, and one thing that is kind of related to this is that ideally you would also like to have a jet definition that is rather robust. What I mean by this is that, for instance, for a person that does fixed order, it's NLO or an XMX leading order, you maybe have 1, 2 emissions that you're modeling. Computing jets on the basis of this, or including a whole shower of partons after it, with or without hadronization, or ultimately on the experimental side at the base of detectors, you would like to have physics conclusions that are invariant with respect to at which stage or which picture you apply this jet definition. Right? So in a way, you want a robust definition of a jet. Okay, so now that I've briefly motivated why jets are important and also got the point out of the way that they are, however, fundamentally ambiguous objects, let me give you a brief outline of the 4 lectures that I prepared for the school. So today I will be discussing about QCD more in general, trying to get everyone on the same page, and then highlight some of the basic properties of QCD, and ultimately try to understand how these jets actually emerge from QCD. And in the next lecture, we will then discuss the soft and collinear singularities and infinite safety. The third lecture, I will introduce the jet algorithms, which are the jet definitions. And in the last lecture, I will take some time to cover the topic of jet substructure, which of course is a very big topic. So this will be only a glimpse. But I think this is already very instructive to somehow get an idea of the underlying principles that go into these kinds of calculations and thoughts. Okay, so let's dive in. As I said, in this first part of the lecture, I want to see how jets emerge. After all, in QCD Lagrangian, we don't see any jets. It's all about quarks and gluons. So how do they come about? And are they automatic or are they an accident? So this is the question that we like to answer. And then also discuss a bit about jets in a hadron collider environment. As I already said, everything starts with the QCD Lagrangian. Essentially, this is a spin 1/2 quark matter with imposing a local SUN gauge symmetry where n is 3. And in the first line, we have the the fermion content in a way. So we have the sum over Q, where Q are the quark flavors going from up, down, strange, charm, bottom, and top. We have the typical Dirac Lagrangian with the covariant derivative. I've written the quark mass term here in the Lagrangian, but in the remainder of these lectures, I will basically completely ignore its masses. And the covariant derivative is given here at the bottom. I think this should be very familiar to everyone. And this introduces the gluon field with an index 8 that runs from 1 to 8. So there are 8 different gluons which are dressed with the associated generators in this covariant derivative, which are just given as 1/2 times these Gell-Mann matrices. In my convention, the normalization is chosen such that TF or TR is 1/2. And in the bottom half, we have the gluon part of the Lagrangian with the field strength tensor. So these first 2 terms should be familiar from QED, and this last term is, as we all know, the additional term we get in case of non-abelian gauge symmetries, which induce self-interactions among the gluons. Okay, and I should have said, yeah, the quarks, they come in 3 colors. I labeled them red, green, blue here. So think of them as a vector. So from this Lagrangian, I can immediately derive Feynman rules. Here are a couple of them summarized. First, we have the gluon QQ bar vertex, and the associated expression is the one here, coming with this, with the generator. You can also put color flow picture to this thing. So if I imagine T1, which is essentially the Pauli matrix wedged into the top left corner, you can see that the application of this generator, what it does is essentially flips a red and a green quark. So in this picture, the gluons actually carry color and anti-color. Let's see, I'm doing the time. Okay. And here we have the 3-gluon vertex. This comes with the structure constants FABC, or the generator in the joint representation. Let me just, for later convenience, highlight some color factors that we will look at. So one is for a gluon emission from a quark line, which is equivalent to this loop diagram, and gives you the quadratic Casimian fundamental, which numerically is 4/3, so you know, and as well the gluon emission from a gluon line, in which case we get the quadratic Casimian joint, which is this NC, so 3. So here, just by looking at the color factor, first of all, I should note that as you would hope or expect, color is conserved. Another point is that just looking at the numerical values, the gluon is has almost twice as much color charge than the quark, which I guess is not so surprising considering that we have this picture up here where the gluon carries color and anti-color. Okay, one very important feature of QCD is the running coupling. So alpha S is defined as this GS squared that I had before divided by 4 pi. And after renormalization, this has a dependence on this renormalization scale mu, and its dependence is described by this RGE evolution equation. So essentially the logarithmic derivative of the logarithm of alpha S gives us the so-called beta function, which I can expand in powers of alpha S, and it's actually known up to 5 loops. For our purposes, all we need is beta naught, and it's given here. And its sign, as we all know, is responsible for the properties of asymptotic freedom in QCD. This NF that appears here gives us the number of light quarks. We always have 3, so UDS are always considered light, but depending on the scale, this can go up to 6 even. And at this lowest order, we can actually write the running or solve it in a closed form quite simply. I guess this is a formula that everyone is quite familiar with. One can alternatively write it in the way done here by introducing this lambda QCD value, which kind of indicates the breakdown of the perturbative description of this running equation. So if I plot this running of alpha s against the scale, we see that as I go to higher scales, the coupling decreases, which is exactly the property of asymptotic freedom. So at short distances, the quarks and gluons are the proper degrees of freedom to use. Whereas if I go into the opposite direction, the coupling increases, ultimately resulting into confinement. So at very long distances, the objects or the QCD degrees of freedom that I should be concerned about are the hadrons, so the mesons, which are QQ bar, bond states, and the baryons, which are 3 quarks. And the numerical value of this lambda QCD is somewhere around 200 MeV. The alpha S value is typically quoted at the Z mass, which is at 91 GeV. And here the value is somewhere around 0.118. Very good. So this kind of already gives us the picture of how we had these gluons that ultimately converted into hadrons from before. So we see that at shorter distances, we should be talking about quarks and gluons, and then there's a transition that happens for hadronization. So one question you might ask here is that how is it guaranteed that actually the direction of my hadrons will actually maintain the direction of the partons that I had before hadronization? And the very short answer is that it's very cheap to create QQ bar pairs out of the vacuum, and because of this, largely the hadrons will follow the same direction as my partons. Very good. So we have a little bit the last part of this jet picture, kind of. Let us move on to the bit that involves the quarks and gluons. Why do the jets look like we see them? And for this purpose, let me look at the real emission. Change the color. So let's consider this parton, this 2 to n scattering, and attach another emission to this. So we keep particle Pi, but we consider the emission of a parton K from this at an angle theta, let's say. What happens is then that this propagator here goes off shell in a way. So it's Pi plus Pk, the momentum flowing. So if I just focus on this propagator, what we have is just 1 over Pi plus K squared. I can also note that Mi, as well as this new emission, that these are massless particles. In which case, this is just 1 over 2 times energy of I, energy of this emission K, 1 minus cos theta, energies, cos theta. Because this is just 2 Ti dot K. And what we observe is that that this amplitude can be strongly enhanced in certain limits. So one limit is the soft limit. where either the energy of EI goes to 0, or the energy of this new emission goes to 0, we see that then this denominator vanishes, and then essentially this amplitude blows up. And there's another limit in which this propagator can blow up. This is the collinear limit, where the angle theta goes to 0. As then cos theta goes to 1. And again, I have a blow up of this propagator. Very well. If I do this more properly, and I will do this in the next lecture in much more detail, and also include the phase-based measure that is associated with this emission of this additional particle, and go into the very simple limit where the emission is both soft and collinear. So that's the simplest limit you can take. Then you can show that the emission probability goes like dE over E and dE. So what does that mean? It means that once I have this kind of a configuration with, in this case, 3 hard partons, right, which go into these 3 directions, this, first of all, I have the property of asymptotic freedom. Which tells me that at these high scales, I'm allowed to apply perturbative QCD for the description of the process. And we have this emission pattern that I didn't derive, which we will derive next time. But which tells us that emissions are preferably going into the direction of these hard lines, or if not, they are likely more soft. So what this means for us is that in this perturbative regime, these hard particles will emit additional gluons, let's say, that will preferably go into the direction of this hard particle, because the emission probability went like d theta over theta, so it prefers small angles. So the same goes for these kinds of legs. Okay, apologies for these very horrible drawings. And if there are soft emissions, which are can also be enhanced, there's no per se constraint as to where they should emit. But that's also something that is enhanced by the emission probability. So in general, when I start with this hard configuration in this so-called perturbative parton shower, so say parton shower picture, this will be dressed with additional emissions that are collimated along these hard lines with fuzzy large areas of emissions. Then ultimately what will happen is that at larger times, we have this property that alpha s increases, which means that hadronization will take place. So this happens at the later stage. And these partons will be then converted into hadrons. And there's no fundamental theory describing this. There are only models. So essentially there are 2 out there. One is the string, the Lund string fragmentation model, and the other one is the cluster fragmentation model. But both of them kind of rely on the fact of popping out QQ bar pairs out of the vacuum. So in the string fragmentation model, you have somehow this QQ bar that is connected by such a gluon flux tube. And as you take these guys apart, the potential energy increases until you eventually pop out a new Kuiper pair out of the vacuum. And given that the masses of up and down are much smaller than lambda QCD, it is very cheap to do this. Similarly, the distortion in like the direction that this kind of process induces is also small compared to lambda QCD, which anyway is the kind of error estimate we had on this whole modeling procedure. And this is the reason why also after hadronization, we expect their directions to be well aligned within lambda QCD or lower with the initial hard radiation. So this is a summary of the slide in a more pretty handwriting, and then what I can do live. So these are the perks of these online lectures, that you can prepare the slides in advance and then fix up your horrible handwriting. Okay, now what I've shown you, so what we've seen ultimately is that that the emergence of this picture of a jet that we had at the very beginning of this lecture, right? This is a event display of the spray of collimated particles. That this is by no means an accident. It's actually an emergent feature from QCD. This is what you expect, looking at the emission probability and how alpha S behaves, basically. So far, I've only looked at the jet in its isolation, but when I look at Hadron Colliders, there's a whole environment around this jet which can impact it by quite a bit. So let's consider this for a second. So again, I have my hard parton directions here in black. As you already seen before, this will induce this perturbative parton shower. So induce additional emissions that are mostly collimated around the original hard parton, which is called final state radiation. But now I also have incoming partons, which are also allowed to emit gluons if they want to. And these are called initial state radiation. This kind of separation is oftentimes not possible. So it's just a little bit of a rough classification of different types of radiation that can happen. What else can happen? So within the proton, other partons or the proton remnants can also undergo the scatterings, right? And so they can also produce some QCD emission. And these are called multiple parton interactions or underlying event. Very good. But this is not all. The last one is more of an experimental issue. Well, not an issue, but what we are doing at the LHC is we're not just colliding single protons, we're actually colliding a whole lot of bunches of protons, right? So whenever I have a bunch crossing, there can be multiple protons that undergo a scattering and produce additional emissions. So let me draw some additional proton interactions into this picture. These kinds of scattering reactions, they are called pile-up. And at LHC, the typical number of scattering reactions of this type that I can have is somewhere around 10 to 100. But ultimately, when we go to the high luminosity phase, where we increase more and more the luminosity, these number of pileup events will also increase and can go up to 1,000 of pileup events, and then this will become one of the challenges. And last but not least, we already said before, we have then this whole hadronization happening at the end. Very good. So let me draw a little cone into this picture, kind of saying, defining the region of particles which I want to take into account for my jet. So this is the jet that I've identified. Then what we see is that, first of all, it better capture the hard parton, because that's ultimately what I want. But it should also capture the radiation from it. So we want the hard parton and the radiation from it, because that is the proxy for the scattering that happened here at the very beginning, right? I want to capture whatever happens after. Now that's good. However, since I've chosen a finite cone size, there's always emission that I will not be able to capture. So even this fine state radiation, that cone go into direction that goes outside of the cone. Similarly for the hadronization, the hadrons can escape this cone. So I inevitably always have some loss of this emission that I actually wanted to capture. But that's not all. I can have other stuff actually contaminating my jet. So if I look at this initial state radiation, this can so happen to end up in this jet that I'm interested in. The same goes for the MPI emissions or from pileup. So there's a plus additional contamination. So let me convert this to a pretty picture where I also spell out what all these abbreviations mean. So as I said, what we're after, or what we want to measure is basically this first term, but I will have a loss and I also have contamination. And then what you see is that I could capture more of the emissions by making this cone size larger. But at the same time, if I do that, I will increase the contamination that I get. And so if I want to decrease the contamination, I would like to choose this cone size smaller. And all these contributions also contribute at different energies. So both final state and initial state radiation typically give radiation somewhere around the hard scale of the process, whereas multiple MPI, pileup, etc. Are more in the GeV region. Hadronization, of course, lives somewhere around the lambda QCD. So changing R will, with these kinds of energy dependencies, will have a very non-trivial dependence on how the jet is reconstructed. So this highlights, I hope, that there cannot be a single best jet definition. There's always going to be a trade-off. And the choice of the jet definition always depends on the application that you want. Right? And we will look at this exactly at this picture again in more detail once we introduce the jet definition and look at how you can choose, for instance, the best cone size and things like this. Okay, so now that I've already introduced the Hadron Collider, let me also introduce the kinematics that are suitable for this. So given that I'm colliding hadrons, and I have so-called parton distribution functions, which tell me with what kind of probability I will get a parton out of this proton that carries some momentum fraction x1 and x2. But I don't know, I cannot experimentally set up the collision in such a way that I can fix this x1 and x2. These are distributed according to these PDFs. So the platonic center of mass frame does not coincide with the hadronic center of mass frame, and it's different event by event, and they're all related by boosts along the beam direction. So it is very convenient at Hadron Colliders, therefore, to choose variables that are either invariant under such boosts or transform very simply. So the choice here is the transverse momentum, the so-called rapidity, and the azimuthal angle. The first and the third are actually invariant with respect to such boosts. In the case of the rapidity, it does transform, but it transforms very trivially. Right? So if I do this boost transformation with the velocity psi, the transformation is just rapidity plus psi. So these are the typical variables that will be used once we talk about Hadron Collider observables and things of that nature. Here at the top, you also see the relation between the rapidity and the scattering angle, theta. I should have probably drawn theta. So theta would be something like the angle to the beam axis. So you see central rapidity, this is how we call it, is around rapidity equals 0, and that's a 90-degree off from the beam direction. Rapidity 1 is 40, rapidity 2 is 15, rapidity 3 is 6. So you see the beam direction ultimately corresponds to rapidity going to infinity. So one thing that we then immediately notice from this boost transformation for the rapidity is that rapidity differences are invariants. So what we can do is we can define a boost invariant distance measure, which we call delta R. Delta R squared is given as the rapidity difference squared plus the azimuth angle difference squared. So if I imagine taking the cylinder, cutting it, and unrolling it in this phi rapidity plane, this delta R constant then corresponds to circles in this area. Now, one question they might ask is how this delta R actually compares to the standard opening angle that we all know, like delta omega, which is related to theta, the scattering angle. And you can show that delta R squared is essentially just given as cosh squared rapidity times delta omega squared. So in the central rapidity region, so here around rapidity equals 0, both of them are roughly equal. Now, however, as I go to the more forward region, so with forward we mean larger rapidity in magnitude, what we see is that the delta R is rescaled by cosh. So the effective circle corresponding to delta omega squared, you basically shrink it as you go to more forward regions. And this is a property that is very, very useful. So if I look at initial state radiation, I've given you without derivation this kind of radiation pattern. We have dE over E, d theta over theta. I can convert this to the Hadron Collider parameters, and then you can do this as an exercise and show that this just is the pt over pt times d rapidity. So this means in this rapidity variable, these kinds of emissions are actually completely uniform. So by effectively choosing this opening angle smaller in the forward regime, what you accomplish is that the contamination you get is roughly uniform across rapidity. So this is a very nice property to have if you, especially an experimentalist, and want to correct your jets for these kinds of contamination effects, if irrespective of the rapidity region, roughly the contamination is uniform. Okay, so this was the last thing I wanted to cover. Yes. So Let me end here. Hope I did not go too much over time. No, perfect. 45 minutes, I think. And in the next lecture, we will continue on actually looking at exactly deriving this radiation pattern and what it means. So you might say, well, this is actually a divergence that is happening here, right? This diverges logarithmically. You could put yourself into the position saying, there's a natural cutoff in QCD, which is lambda QCD. Sorry, not A, lambda QCD. Similarly, for the angle, we could argue, oh, this should be of the order of lambda QCD over the hard scale. So there's actually not a singularity. But if you do perturbative calculations, there are genuinely similarities, and these are things that you do not want. So in the next lecture, we will discuss what these similarities mean and how they disappear for a certain class of observables, and why such observables are preferred choice. Okay, so let me stop the recording here.